So this talk is very similar to my PhD defense, so those of you who downloaded the slides, you already know everything. Now you get the audio comments. It's on approximate shortest path and distance queries in networks, so I will assume some graph theory knowledge. Just interrupt me if you have some questions. So the outline of the talk is going to be the following. I will try to introduce the problem by motivating why it should be interesting for many people, and then I will give 3 results and conclude. And the motivation is the following. We're given some kind of a network or a graph. For example, it could be a map, say a map of Korea or a map of the US or the map of a large continent, and we want to find the shortest path between 2 nodes. Say between these 2 red nodes. Oh, now I can. Okay, between these 2 nodes. I'm not yet used to this fancy device. We want to find the shortest path between these 2 nodes, and well, I'm sure you all know how we compute it. Well, Dijkstra's algorithm will do it for us, right? Bam, here it is. Found the shortest path. So now, how does Dijkstra's algorithm compute the shortest path? You start at 1 node, say we start at the source here, and we add nodes to some priority queue. And at each step we expand with the node that is at the shortest distance. And if we want to be faster, if we just care about the distance between 1 source and 1 target, we can basically start at both the source and the target simultaneously. And how long is this going to take? Well, roughly linear in terms of the graph size, in terms of the number of nodes and number of edges. So if I was to find the shortest path from Tokyo, where I just came from, to KAIST, to this wonderful institute, then it would be quite difficult because, well, the world map contains many nodes, many edges, and linear time in this big graph is way too long, right? And it actually was much faster. I just asked Google Maps, and it would output me everything. Well, actually, Sommer gave me the direction, so I didn't need this. But if I needed such a path, then it's not going to take linear time. Or even if I use some GPS navigation system, it's not going to take linear time to compute it. It's doing it much faster. And this is what we want to do. We want to efficiently find the shortest path between 2 points of a network. Could be a transportation network, or also like modern applications like social networks. If I need a favor from one of you guys, then I would probably go through Sommer because he is now a connection of mine, and then find the shortest path to one of you guys. Or in computer networks, if you want to send a message through a network, well, you would rather have it sent along the shortest path to arrive quickly. And some people say that there are applications in biology as well, in like protein interaction networks. I don't know whether this is true, but it could be. So what we want to do is we want to pre-process a graph G or some network, and we will assume that it has n nodes and m edges for the rest of the talk. And we want to create some kind of a data structure using which we can efficiently answer distance queries or shortest path queries. And by distance query, I mean we ask for the distance between a node U and a node V. So this is pre-processing time, and this is the query time. We will distinguish these 2 things. And I will relax the notion of the distance a little bit. I will say, well, we can also compute approximate distances. What do I mean by approximations? Well, say the original distance is here denoted by dg between u and v, so the distance between u and v in the graph. And we want that the approximation, the result here, should be at most alpha times the original distance plus beta. So we could have some multiplicative stretch alpha and some additive stretch beta. So it would be best if we had alpha equals 1 and beta equals 0. Then the result would be perfect. And also note, please, that we never allow that the distance is too short. We always want to output something that is a bit too long maybe, but not much too long. So this is a very standard notion for approximation algorithms, of course. As you can imagine, the shortest path problem has lots of related work. Dijkstra's algorithm was published in 1959. And actually there was a survey on shortest path algorithms in February 59, that listed like nine algorithms for shortest paths. It didn't contain Dijkstra's algorithm because it was just published then. And in December 59, there was another survey article saying like, oh, by the way, the guys in February, they forgot. They forgot some important algorithms. They list some more, and they also didn't list Dijkstra's algorithm. So there's lots of important algorithms and lots of results on here. And right from the beginning, the practical focus was on transportation networks. And theoretical results, they distinguish basically between general graphs and some restricted graph classes. And I will give a brief overview of the results in here. Let's start with the transportation networks, with the practical results. Right after these networks were introduced, this graph theory was started in the 60s or early 60s. They started working on this, and the main focus, as I said, was on transportation networks. And there was big progress recently. In 2006, there was a Dymax implementation challenge. And what they wanted to do is basically they solve this problem for very large networks, say continental-sized networks, which would contain roughly, say, 15 million nodes or 20 million nodes. Now, the pre-processing they achieved was, say, tens of minutes for a really large road network, say, size of the US or Europe. And the query time would be like 1 million times faster than Dijkstra's algorithm. So, but if you were to solve this problem, one thing you could do is, well, pre-process everything. Let's just compute the big table. For all pairs U and V, we compute the distance. But this is going to take you much longer than this couple of 10 minutes if the graph has millions of nodes. And also think of the space. Millions of nodes squared. It's not going to fit on a DVD, and you can't put it in the car to have this map software. So the space is also a big issue here. But of course, these road networks are much easier to handle. You don't have to compute the distances between all pairs. You could just, for example, take the big cities, or just use some highway structure. So for these special types of graphs, we can do much better than pre-processing, just computing a big table. So what they use some ideas from geometry, and the coordinates are often known for road networks, and they have hierarchical structures, as I said before, like with highways and stuff. And these heuristics work very well for these sparse road networks. In theory, however, for general graphs, it looks much different. Let's, for the moment, assume that the graphs are unweighted. Now, first two lines are the classical results. One is we could do all pair shortest path, which is that we create this big distance table I mentioned before. So the pre-processing time is going to be proportional to the number of edges times the number of nodes. And the space is going to be quadratic. But the query time is very efficient. We just make one table lookup. And the result is going to be optimal. The other thing is we could also be lazy. Say pre-processing, we just sleep. We don't do anything. And the space is basically, well, we just store all the edges. And at query time, we run Dijkstra's algorithm, or for unweighted graphs, a breadth first search is going to be enough. And these are optimal results. Now, if we consider, what we want to do is something in between these two results, right? And the most important result in this area is by Thorup and Zwick, which was in 2001, which is these approximate distance oracles. So this tilde here denotes that I ignore logarithmic factors. What they prove is you pick any integer k, and what you get is a distance oracle that will have stretch 2k minus 1. So let's, for the moment, say we pick k equals 1. What would we get? K equals 1 would give us a 1 here. So it would be optimal. Now if you put a 1, I put 1, yes. If I put a 1 here, then we get m times n to the 1 plus 1 over 1, which is n squared, and query time order 1. So we basically got this all pair shortest path solution. If we put k equals 2, then we will get stretch 3 here. So paths could be up to 3 times longer than the original distance. And the space is going to be n to the 1 plus 1 over 2. So n times square root n. So if you have your graph with a million number of nodes, then the space is going to be 1 million times 1,000, which is still pretty big. And all you get is stretch 3. So imagine if I was taking a stretch 3 path from Tokyo to KAIST, I would probably not be here yet. It would take some more time, right? But unfortunately, what they prove is this trade-off, which sounds pretty bad here, it's actually tight, it's optimal, best possible. So this is the lower bound, the matching lower bound. You have to read from right to left now. So if we want the stretch to be less than 2k plus 1, then the space we need is n to the 1 plus 1 over k. So let's again set k to 1 here. Then it says if we want stretch less than 3, then we need n square space, which is kind of surprising, because it doesn't even say anything about the query time here. It just says if you want this kind of stretch, then you need this space. So they basically say that there are graphs which you cannot compress. Even applying WinZip twice or 3 times, it's not going to help. It takes a lot of space. You have to store it using a lot of space. This is their lower bound. And for the other performances, they don't prove whether it's optimal or not. And indeed, some other guys improved their query times and their preprocessing times subsequently. But yeah, the lower bound is kind of disappointing. So for general graphs, we can't do very well. Let's see whether for some restricted graph classes we can do something. Well, for example, like planar graphs, like these road networks. Apparently in practice we can do well. And indeed, for graphs with bounded tree width, for example, or for planar graphs, we can do very well. So for bounded tree width graphs, the space is going to be linear, and the query is going to be exact. So the result is going to be perfect. And for planar graphs, the space is going to be, again, I hide polylogarithmic factors here, the space is also going to be roughly linear, and the stretch is going to be 1 plus epsilon. This also holds for minor free graphs and graphs with bounded doubling dimension. So for some restricted graph classes, we can do very well. Well, others can do very well, and I read their papers. Now let's see. We had this restrictive lower bound here, but we had also these promising results here. The question is, can we do the same thing for all sparse graphs? Can we get some efficient distance oracle for all sparse graphs? So recall that the lower bound by Thorup and Zwick said we cannot compress the graph. Like applying WinZip 3 times, it doesn't help. But if the graph is already sparse, then we don't need to compress it. It's already small. We just need to find an efficient query algorithm somehow, maybe build some additional structure. So for sparse graphs, their lower bound doesn't apply at all. Maybe we can do something. And this is the question we tried to answer in the first part of the talk. And if you remember only one thing of the first part of the talk, then it should be that the answer to the question is no. So we proved that for sufficiently large graphs, any distance oracle with stretch alpha and query time at least t. So this t is in the cell probe model. I will explain in a second what it means. Any distance oracle with stretch alpha and time t requires space at least this. Okay, this looks like a weird expression. Let's see it in context. So what Thorup and Zwick prove, if you want to get stretch less than 2k plus 1, this is the space you need. And we already know that for sparse graphs, we cannot do anything without the query time here, because we could just store the graph. So what we show here is that if the stretch is going to be less than or equal than alpha, and the query time is t, then this is the space we need. So compared to Thorup and Zwick's result, they had some constant factor here, and we have a constant factor here, which is arguably much worse. But yeah, this is the only thing we can prove here. Let's compare some more. The hard graphs in the lower bound by Thorup and Zwick are very dense graphs. And I want to argue that we don't care about dense graphs. Well, maybe we do care about dense graphs, but in terms of distances, I believe that we care more about sparse graphs. For example, if we take these road networks, or if we take the road networks and we add some train connections on top of it, and some plane connections if you want, then it's still sparse, because you won't get any complete graphs there. But yeah, if we just get sparse graphs, then then we can still not do anything. So in this proof, the degree of the graph is going to be polylog n. So it's not actually super sparse. They don't have constant degrees, but like polylogarithmic in n. This is an open question to improve this to constant degree graphs. So what we knew before for sparse graphs was that, well, the space you need is n times polylog n. And what we know now is that the space you need is n to the 1 plus epsilon, which is much more than just storing the graph. It means that we have to compute a lot of additional structure to have efficient query time. And for the remainder of the first section, I want to give you a brief outline of how the proof works. And the proof is a reduction from a distance oracle problem to a communication protocol. So this is a reduction to some communication complexity problem. And the protocol we generate using a distance oracle will then efficiently solve a communication problem. So this is the second step. And since this communication problem is very hard to solve, there is a known lower bound for this communication problem, we know that we have some kind of a contradiction. We know that there can't be an efficient distance oracle. So this was a lot of information for the first slide, but I think it will get clear in the following, if you haven't seen it before. So the problem we're looking at is called lopsided set disjointness. Alice and Bob both get a subset of some universe. So think of it as the universe is like a big set of sweets, and both Alice and Bob get some sweets. And they want to know whether they have some sweets in common. So their goal is to find out whether the intersection of their sets is empty or not. So say Alice gets some chocolate and Bob gets marshmallows and some different chocolate and whatever, some ice cream. And it's not fair. Bob gets a much bigger set than Alice. They want to find out, using some efficient protocol, whether they have some sweets in common or not. And it's known that if they want to solve this problem without any error, then the protocol is going to be very long. So they need to communicate a lot in order to solve this problem. But what could they do? Alice could just tell Bob everything. Hey Bob, by the way, I got chocolate, I got this, I got that, I got that. It would take forever. And then Bob would know whether he has something in common. Of course, he could, before, when Alice mentions something he got as well, he could say, okay, I already have it, we're done. But in the worst case, this is not going to work, right? So either, what the lower bound says for the problem is basically either Alice sends everything or Bob sends everything. Almost, up to some constants. If you want to solve this problem, then either of those has to send everything, which means that this protocol is very long. Now what we do is the following. We let Bob simulate some kind of a data structure. In our case, it's going to be a distance oracle. And Alice is going to ask queries to this distance oracle. And now this is about the cell probe model. So in the cell probe model, we have the database here. So this is the database, and Alice is going to ask queries. And well, how do you specify if this is a large array, what you want to access? This is a large array, and you have to somehow specify which cell you want to read. So using whatever 32 bits, you say which cell of the array you want to read. So in each step, for t rounds, if the data structure has size s, Alice will say which cell of the array she wants to read, which takes her log s bits, and Bob will reply with the corresponding cell of the data structure. So this is our reduction. If we can find some nice queries to some distance oracle, then we can get some communication protocol out of this, right? And of course, it's not going to work with the sweets. So the universe is anything they want, but we want to have this some graph setting. So what we do is we apply a bijection from the universe, which were the sweets before, to the edge set of a graph. So both Alice and Bob apply a bijection f, which maps their sweets to some edges of a graph. This idea is, by the way, from Petroshku. So what they get, they both agree on this graph. And this graph is an expander graph which has the following properties. It has n nodes and polylog degree, and it has girth log n. So what's the girth? It's the length of the shortest cycle. Why would we care about this? You will see it in a second. But it's important that it doesn't have any short cycles. The graph doesn't have short cycles. So since this graph is sparse, there must be an efficient distance oracle for this by contradiction, right? So the proof is going to be by contradiction. We assume that there is an efficient distance oracle. Alice and Bob both know this graph, and now they get their suites, and they apply the function f. So Alice gets a set of edges of the graph, and let's assume that these edges form paths. I guess you can already see where this is going. So Alice gets a set of paths, and Bob also gets a set of edges. So this is the setting. After applying the bijection, Alice will get this set of paths, and Bob will get a set of edges. Now what we want to do is we want to answer distance queries. And using these distance queries, we want to find out whether the sets of edges are disjoint or not. Because applying a bijection, of course, doesn't change the intersection function. So how can we find out whether these sets are disjoint or not? Well, Bob is going to apply the following transformation. Bob is going to remove the edges he got from the original graph. So Bob is removing the edges he got. You can see here, this is the set he got, and he removes it from the original graph. And now Alice is asking distance queries. Let's look at the green query, for example. If Alice asks this distance query, then what's the answer going to be? Well, the original distance is 2. And we created an alpha approximate distance oracle. So what's the result going to be? At most, 2 times alpha. Let's look at another query here, say the blue one here. Okay, there is one edge out. Now here's the property of the graph, that the graph does not have any short cycles. It has large girth. It means that because one of these edges is out, there is no short alternative. So to go from here to this node here, we will have to take a very long path, basically following all these guys here till we finally arrive, which is going to be much longer than 2 times alpha. So if Alice gets a reply to the blue query, she will know that one of the edges was missing, and that for this reason the intersection was not empty. And the same also happens for the red query here. As you can see, in the red query even both edges are missing, and the path is also going to be very long. So this is the idea. So after querying all these distances, Alice and Bob will know whether their sets intersect or not. Now, just to rephrase what we just saw before, the original distance in the graph is going to have length L. So we assume that Alice gets paths of length L. Now if one of the edges is missing, then the distance is going to be bigger than alpha times L. The result of the distance query, I mean, is going to be more than alpha times L. And otherwise, it's going to be less than alpha L, or at most alpha L, if all the edges of the path are in the edge set of G prime. So using one distance query, Alice and Bob can basically decide whether for the edges of this path they have an intersection or not. So to sum up the first contribution, what we saw was that while Thorup and Zwick proved that for dense graphs we need big distance oracles to achieve anything meaningful, we proved that even for sparse graphs you need a lot of space. And there is an important open question here which I want to ask you, which is, well, let's say we care about linear space, because these graphs are huge, and basically all we can do is linear space. As soon as we have n to the 1 plus epsilon, it's not going to fit on your memory anymore. So if we want to get linear space here, what we can do is, well, we can set either alpha or t to log n. Or, well, both of them to square root log n or something. But if this product here is log n, then we will get linear space. in the lower bound here. Now let's look at the upper bounds. If we do this in Thorup and Zwick's oracle, we could, for example, set k to log n. Then what we get is linear space, well, log n times linear, but that's fine, and log n query time and log n stretch, which is nice, but, well, not optimal, because here we could have that only one of the two is log n, and not both. And indeed, Manor and Mendel and Naur, I always say that wrong, Mendel and Naur proved that you can reduce the query time down to constant, even if your stretch is log n, and then you would get linear space. I want to ask you, can we do the other thing? Can we get query time log n and some constant stretch? Any constant is fine, 1,000 is fine, but I don't want to have log n here. It only has to work for sparse graphs. This is the question I've been trying to solve for a long time. Maybe one of you will find it. Let's go to the second point. How am I in time? I don't know. Already spent a lot.
Half an hour.
Okay, good. The second one I want to look at is power law graphs. We've seen this for general graphs, these results, and we know that for some classes of graphs we can do very efficient distance oracles. So for bounded tree width, for planar graphs, and for road networks. And the question is, how about other real-world networks? The ones I mentioned on the slide number 4 maybe, which are like social networks or computer networks. They are non-planar, a bit more complicated, but still sparse. So what I want to talk about is power law graphs. And a power law distribution is the following. Let's say we have a random variable d and a power law exponent tau between 2 and 3. Then the probability that d equals x is proportional to x to the minus tau. So if we take this d to be the degree of a node, then we will have that the probability that the degree is x is proportional to the x to the minus tau. It means that you have a very large probability to have a small degree and a very small probability to have a high degree. So if we look at the degree distribution of these kind of graphs in a log-log scale, so this is the degree, and this is the number of nodes with a certain degree. Number of nodes. And both are on log scales. Then this will look something like this. So for a large degree, we only have very few nodes with this degree, and for smaller degrees, we have lots of nodes with this degree. So these are the power law graphs we're looking at here. And apparently they are quite common. For example, for social networks, some people believe that the internet is also a power law graph. Some people believe that it's not. We don't know. Protein interaction networks, or the citation graph, or web graphs. So many real-world structures do have these kind of degree sequences. It would be interesting to have distance oracles for these kind of graphs. And there are many different models for these graphs. Of course, we cannot just say we do it for any graph with this degree sequence. We need to somehow model how these real-world networks look like. One of the most famous models is the preferential attachment model by Barabasi and Albert, and there are many other models. And we will look at the model by Fan Chung and Lingwan Liu, which is called the expected degree model, which works as follows. Oh, no. Sorry, let me skip this for a moment. So these complex networks, they don't have bounded tree width. They're not planar, they are not minor free, and they're not road networks. So all of the previous approaches fail. And, well, the only thing we could do is we could just apply a general distance oracle, such as the one by Thorup and Zwick we saw before. And there has been experimental evidence that, indeed, the distance oracle by Thorup and Zwick works very well for these kind of networks. What do I mean by it works very well? Now, the space is actually much smaller than what you would expect from their bound. So recall that for stretch 3, what they needed was space n times square root n. And what we prove now is that actually the space is much smaller indeed. We prove that the space is n to the 1 plus gamma, where gamma is some function of this power law graph. So the experiments that show that this Thorpe and Zwick power distance oracle works very well for power law graphs, we now give some evidence why it works very well for these Junglu random power law graphs. Now let's look at how Thorpe and Zwick's distance oracle works. I will have pictures for all of this. Let's simplify it. Let's just have k equals 2, which gives us stretch 3 distances. What they do is they sample nodes at random. They sample square root n nodes, and they call these landmarks. So if this is our graph again, then A, B, C, D, and E would have been sampled at random, for example. And then they do a single source shortest path search for each landmark. So from there, they start the single source shortest path search. So for example, for landmark B, they would, after this search, would know the distance to all the other nodes in the graph. Now, after this step, if we look at a node that is not a landmark, so after this step, it would know the distance to all the landmarks. So A, B, C, D, and E. And in particular, this node would know which node is its closest landmark. So for example, for this node, it could be A, I guess. Maybe D? It's 1, 2, 3, 4. 1, 2, 3. Okay, so this is an unweighted graph. It's not Euclidean. So indeed, the A is the closest landmark for some reason. Yeah. So for this graph, for this node, A would be the closest landmark. And the third step of pre-processing is the following. They compute a ball for each node U, which contains all nodes that are closer to U than U's nearest landmark. So if we look at this guy here again, then it would compute the ball, so which grows until it hits the landmark. But actually it stops just before. It just contains all the nodes that are closer to U than U's landmark. At query time, what we do is, if we are asked for distance between U and V, we check first if V is in U's ball. And vice versa. We also check whether U is in V's ball. If so, we return the exact distance. And otherwise, well, we go from U to V's landmark and from V's landmark to V, because we pre-computed this information. So now let's check for a query. So first case, we have that, well, they are in each other's ball somehow. It will get the exact distance as an answer. In this case, however, you see the ball of this node is empty. Well, it only contains itself. And we're just out of this one here. So if we go from this node to this node's landmark, A here, so we go all the way to A, and then finally to the target, it's going to be pretty long. How bad is it going to be? Well, they claim it's going to be at most 3. This is the stretch proof. It's fairly simple. I let you think for a moment. So this is U and this is V. And we assume that they are not in each other's balls. So this is U's landmark, and this is the ball for U. And this is V's landmark, and this is the ball for V. And this is what we want to prove. The distance from U to V's landmark and from V to V's landmark. So we actually turn these two, right? So it's an undirected graph. So from U to V's landmark and from V's landmark to V is at most 3 times the distance. So from U we go here and then to V. Maybe this is too easy, but I let you think for a second how you would prove this. If anyone who comes up with a solution, please raise your hand. So let's first bound this part here. Well, it's at most the distance from U to V, right? Otherwise, U would be in V's ball. So this one is done. Now what we want to do is we want to bound this one. This looks somehow harder, right? Well, exactly. It's just a triangle inequality, right? So it must be less than this plus this. Oh, less than 2d uv. And we get stretch 3. Very simple. So this is their distance oracle. And, well, now, why do we get n times square root n space? Well, we selected square root n landmarks, and each node stores the distance to all these landmarks. Now, this is going to take space square root n. And each node also stores a ball. Now, how big is the ball? The expected size of the ball is square root n for each node, because you enumerate all the nodes around U, and each node is selected as a landmark with probability such that the number of landmarks is square root n. So it's selected with probability 1 over square root n. So after square root n times log n steps, you will have a landmark. So this is why the balls are also bounded. So basically the ball sizes match the number of landmarks, the expected ball sizes. This is why they get this space trade-off. Now what we do is we modify this for our power law graphs. And as you may already have guessed, of course we take the nodes with large degree to be our landmarks. We don't use random sampling, but we use these nodes with large degree. So I'm sure everybody in the room would have come up with this idea. The only challenge is to prove that it works. So what we do is we pick these high degree nodes as landmarks, and we want to prove that the ball sizes will have expected size the number of landmarks. So we want to find the right balance between the number of landmarks and the ball sizes. Basically, we want to find this gamma here. And how do we do it? Well, okay, I guess you already believe me that to store the distances to all the landmarks will take space n times n to the gamma. That's a trivial thing because we just selected it that way. The only thing that remains to prove is that the expected size of the ball is at most this. And this is the idea. So when we grow a ball from a node U, then either we detect a node with a high degree, and then we are done. The ball is over because this is a landmark. And if we don't have a node with a high degree, then on the way all the nodes had small degrees. So the ball growth is fairly small. So we have a small ball until we hit the node with large degree, and then we are done anyway. And this is formalized as follows. So let the volume U, the volume of a set U be, oh, I should probably introduce the Jung-Lu model first. Okay, what they do is each node has its degree proportional to a potential. So what they do is they take a distribution that looks like this. It looks like this power law distribution, and each node gets a value out of this distribution, which corresponds to its degree. So each node Vk gets a potential Wk, and then edges are inserted into the graph with this probability. So the probability to have an edge between Vi and Vj is proportional to Wi Wj divided by the sum of all the weights. And they prove that if they use this kind of strategy to generate graphs, then the expected degree is actually this Wk. And you will have this kind of power law graph. And the expected degree is actually concentrated around Wi for a node Vi. What you have to observe here is that usually graphs with large potential are connected together with high probability. So nodes with large degree will connect to other nodes with large degrees. So this is not necessarily the most realistic model, but somehow it works for us. We can prove that for this particular model we get an efficient distance oracle. Now the important lemma we use is the following. If for a set of nodes U, the volume of this set of nodes, let's denote this by volume of U, is defined by the sum of all the W. It works even on blackboards. Amazing. So if we take a set of nodes, we just sum up all their W values, all their potential values. So this volume is basically the potential of a set to make connections. Now, the lemma says the following. If we have two disjoint subsets, S and T, then if they have a large volume, the probability to have a connection between these two sets is pretty big. Basically, if the volume of S times the volume of T is bigger than a constant times the volume of G, where the volume of G is just defined as the volume of, well, the sum of all WK here. So if these two volumes, the product of these two volumes is bigger than C times the original volume, then the probability that the distance between S and T is just the probability that there is no edge between S and T is at most e to the minus C. So this already contains the proof here, actually. It's a very simple lemma, but it already proves a lot. So since we basically just apply this thing, the generation of the graph, for each pair of nodes, right? So for each node in S and each node in T, we apply this, and then since the edges are independent, we get that the probability that there is an edge, that the probability there is no edge, is at most e to the minus C. Now what we do is, well, for S, we pick our nodes with large degree, and for T, we pick our balls. And then we say, well, if the ball has a certain volume, then it's connected to the landmarks. We basically just apply this lemma for all balls. So what we showed in the second contribution is that the high degree heuristic you all came up with is probably good for random power law graphs. Doesn't mean that it works for all these complex networks, but we hope that it does. So this is basically the first approach for sparse graphs that doesn't use any separators. If you've seen the result for graphs with bounded tree width or planar graphs, they basically are all based on separators. And for power law graphs, there is no such separator. It would have linear size, so we don't get any theoretically feasible result. And the preprocessing and the space consumption are very efficient, and the worst case stretch is 3. There is one thing I didn't tell you yet. The experiments also showed that the stretch of Thorup and Zwick's distance oracle is much better than 3 for these power law graphs. And we were not able to prove anything better than 3. Maybe someone else can. I mean, yeah, would be nice. Because as I said before, stretch 3 is kind of disappointing. You never arrive at where you want to go. And in these power law graphs, in particular, the distances are very short. So if you get stretch 3 there, it doesn't mean much. This is what we could prove. Of course, this is for n to infinity, so stretch 3 there means a lot, but for reasonably sized networks, it doesn't mean much. The third one is a practical method, the third thing I want to talk about. And it works for many graphs, including these complex networks. It also works for road networks, and it's very efficient. So the preprocessing is really efficient, but the query time is somewhat, well, we don't have a theoretical bound for the query time. So this is a pretty applied thing here. And it's very simple. I'm sure all of you, you're much better programmers than I am. I'm sure you could implement it in one afternoon easily. You know the Voronoi diagram, I assume. So for a point set in the plane, say again A, B, C, D, E, F, G, we partition the space into regions such that each node is assigned to the Voronoi site that is closest. This is somewhat similar to what we saw in Thorpe and Zwick's result before. Now, we can do the same, the dual. The dual is the Delaunay triangulation, which connects to Voronoi sites by an edge if their regions are adjacent. Now, we can do the same thing for a graph, actually. So we again have our Voronoi sites here, A, B, C, D, E, F, G. And each node is assigned to a Voronoi node. So we pick these Voronoi nodes somehow, and we compute the graph Voronoi diagram here. So each node is assigned to some Voronoi node. Now, if we look at the dual again, the Delaunay dual or the Voronoi dual, it's not going to be a triangulation. Not necessarily a triangulation. It could be a triangulation, but not necessarily. So, for example, we have these weird structures here, right? So before A and D were connected, now they're not connected anymore. So the dual could be pretty weird. What we show is that the dual still has somehow some good properties, some properties we like. The graph Voronoi diagram has been introduced by Mailhorn in '88 implicitly, and then by Erwig in 2000, and it can be constructed in time n plus n log n using Dijkstra's algorithm once. So think about it for a moment. How would you construct a Voronoi diagram? Well, the idea is, so if you're given just one node, it's very simple. This will contain all the other nodes, right? If we're given two nodes, and if we run a Dijkstra search from one of the nodes, it's not going to work. But if we run it simultaneously from both of the nodes, then as soon as they hit each other, you know that there's the boundary. So what we do is we add a dummy node and connect it to all the Voronoi nodes and construct a single source shortest path tree. And then we know the Voronoi diagram. And actually in this step we can also compute the Voronoi dual. Because whenever we cross a boundary, whenever we discover a new node, an already covered node, then we will have an edge between the two Voronoi nodes. So the pre-processing of this method is really simple. We randomly sample Voronoi nodes. Maybe for these graphs we could also again make this strategy of selecting high degree nodes, but we just pick them at random. We compute the Voronoi dual. And at query time, we compute the shortest path between the Voronoi node of U and the Voronoi node of V. Very, very simple. And optionally, we could refine the path by looking at the union of all the Voronoi regions. So there is a picture for this. Say we want to find the shortest path between U and V. This looks familiar to some of you, I guess. It was on the second slide. Now, what we do in the method is, well, we go to the Voronoi nodes, which are here F and C. Now we find the shortest path in the Voronoi dual. The Voronoi dual now is a weighted graph. The shortest path is going to go here. Now what we could do is, well, we could just return the distance from this node here to here plus this distance and be happy with it. Or we could also refine it. Let's say, okay, we refine it by taking the union of all the regions we visited. So it would be this region and this region and this region and this region. So basically we select these regions, and now we start with the original source and the original target again and find the path in there. So this is what the result is going to be if we refine. Now recall that the original result was here, was this path, which had 1, 2, 3, 4 edges. And the new one has 1, 2, 3, 4, 5 edges. So it's one longer. The question is, how bad can it be? And pretty bad, actually. So the theoretical bound is, it depends on the probability of the random sampling. So the expected worst case stretch is if the original length of the path is L, then it could be at most log L times longer divided by something that depends on the sampling probability. And experimental results show that for road networks is very small, and for power law graphs or for its complex networks, where we took some real world data like the DBLP network and some router network and some social network. Oh, that was a DBLP. Yeah, and some others. It's less than 2 for complex networks, and it doesn't depend on L. But we couldn't prove that the stretch doesn't depend on L somehow. Well, how does it work, the stretch proof? If you're still ready for another proof. So if we have U and V here, and the distance between U and V is A. Now, let's assume for the moment that U and V are Voronoi nodes. Just that we don't have to deal with this initial segment. Now, if we have another node here, another Voronoi node V here, W here, that somehow grabs this node into its Voronoi region. So this would be the Voronoi region now. This is the region boundary. Then the Voronoi dual will look somehow like this, right? U is connected to W, and W is connected to V. But the shortest path between U and V would actually just have length A. Would go through this node here. Now, if we... Now, what's the length of the dual path? Sorry, that was too early. What's the length of the dual path? It's going to have length A plus 2 times this, right? So it's going to have length A plus 2, which is, well, the number of edges we had on the path was 2, and the original, the Voronoi distance could be A plus 2. Now, if we have an alternative path in the dual that's somewhat between A and is A plus 2, which is just a little bit shorter than the blue path, but doesn't go through this part here anymore, then we will never find this original path anymore. Even if we do some refinement, we're not going to find it anymore, because we just take this region, and we somehow never go through this part. So there could be some adversary that puts this path and takes us out. So this was if we just had one node on the path. Now what if we have more? Like, it could look something like this. There could be a Voronoi node here, and here, and here, and here, and they're all bad for us, because the path now goes like this. Now the original path had length A, and we had one here, and one here, and one here, and one here, twice actually. So we had 1, 2, 3, 4, 5 edges, and for each of them we add 2. So basically if we have L edges, then there could be an alternative path of length L times A that would destroy everything. Well, I told you that the stretch is not L, but log L. Well, the only hope we have is that some of the nodes on the path are Voronoi nodes. And each node is a Voronoi node with probability P, so the expected largest gap between two Voronoi nodes is proportional to this, using some geometric random variables and the maximum of geometric random variables. So to sum up, the contribution of this method is the preprocessing is very efficient. It's actually much faster than all of these Dimex methods. We preprocess 15 million or 20 million nodes in less than a minute. This is like almost takes that long to read the graph into my memory. And the query time is pretty competitive. Of course, it depends a lot on the probability you use to sample. If your Voronoi dual is small, then you will be very efficient in there. But the stretch is going to be worse. And it's very simple, but it's not exact. And we can actually trade the query time versus the stretch. If we decrease the probability, then we get efficient query time, but worse stretch. So this is something new. This was not possible for the method by Thorup and Zwick. They cannot trade query time for stretch. They can only increase both simultaneously. We can say, okay, you get a bit better stretch, and we get some more query time for it. Something like that. But the trade-off we achieve is far from optimal. But we can somehow trade the two. So to conclude, the first thing we looked at was that there is no efficient distance oracle, even for sparse graphs, with space proportional to the number of edges. But there are still many sparse graphs for which we can obtain efficient distance oracles, for example, for these power law graphs. And in practice, well, we can do even much better. So, thank you very much for your attention. Thank you very much for inviting me, and I had a lot of fun. Thank you.